Today, we're going to take a really close look at schizophrenia, but we're going to frame it a bit differently, not just as a psychiatric condition, but as what it truly is, a neurodevelopmental disorder that has deep, deep roots in our genetics and in the very way our cells produce energy.
So, here's our roadmap. We'll kick things off with a clinical story to ground us in reality. Then we'll dive into the genetic and metabolic factors, zoom in on what's happening at the synapse, trace the disease's progression, look at treatments, both current and future, and wrap up by considering the whole person impact.
All right, let's get started. To really understand the science, we have to first understand the person. Let's talk about what this looks like in the clinic.
So picture this. A 21-year-old man walks into your clinic. He's at that typical age of onset for men, and he says something that just stops you in your tracks. I feel like my brain is broken. I mean, what a powerful way to describe the profound internal chaos that our patients are going through.
Now, when we dig into his history, the pieces of the puzzle really start to come together. You see, over the past year, he's been showing those classic, subtle prodromal signs, his grades slipping, pulling away from friends. These are the things that are so often missed. But then, in the last 2 months, things escalated. He's now in the active phase, with unmistakable positive symptoms, hallucinations, delusions. And that family history? A paternal uncle. That's a huge clue pointing us right toward the genetic piece of this puzzle.
And his story? Well, it's not an isolated one, not by a long shot. Schizophrenia touches about 1% of people worldwide. But here's the number that should really grab you. It shortens a person's life by an average of 10 to 25 years. This tells us loud and clear that this is not just a mental illness, it's a systemic condition that impacts the entire body.
So, let's peel back the layers. Let's move from what we see on the outside to what's going on under the hood. What is actually setting the stage for this disorder at the genetic and even metabolic level?
This, right here, is striking. Just look at the sheer weight of genetics in this condition. We're talking about 60 to 81% of the risk for schizophrenia being inherited. Now, environment matters, for sure, but this tells us the primary vulnerability is really baked into the DNA.
But it's not a simple story like finding one single schizophrenia gene. No way. It's highly polygenic. Think of it as a perfect storm of many different genetic factors. Some are rare but have a big impact, like the 22q11.2 deletion. Others are more common, like variants in a gene called C4a. Put a pin in that one, we'll be coming back to it. And some are even more complex, like pseudogenes that mess with our mitochondrial function.
And you know what? A lot of these genetic clues all point to one critical process, oxidative phosphorylation, or OXPS. This is basically the main power plant for our cells. It's how our mitochondria churn out almost all the ATP, which, as you know, is the energy currency that neurons need for literally everything they do.
And this slide just illustrates the consequence perfectly. A healthy neuron is like a finely tuned engine. But in a neuron affected by schizophrenia, that engine is sputtering. We consistently see in research that key parts of the mitochondrial machinery are working 18 to 35% less efficiently. The direct result? A 20 to 22% drop in energy production. It is a genuine energy crisis at the cellular level. And it leads to all sorts of downstream problems like crippling oxidative stress. So this energy deficit doesn't just happen in a bubble. It has massive ripple effects. Let's see how this cellular power failure leads directly to a breakdown in communication right at the level of the synapse. Okay, so this brings us to a really important question. When we look at brain scans, we often see a loss of gray matter. But when we examine postmortem brain tissue, we don't see widespread neuron death. So, what gives? What is actually causing those changes? The answer is absolutely fascinating. It lies in a completely normal process that just goes haywire, synaptic pruning. Think of it like a gardener trimming a rosebush. During our teenage years, the brain gets rid of weaker connections to strengthen the important ones. It's this beautiful sculpting process that makes our brain circuits faster and more efficient. But in schizophrenia, that gardener goes rogue. Remember that C4a gene I told you to put a pin in? Well, here's where it comes back in a big way. Overexpression of this gene leads to way too many complement proteins floating around. These proteins act like little eat-me signals. They start tagging perfectly healthy synapses, which basically tells the brain's immune cells, the microglia, to come in and gobble them up. The end result is this devastating overpruning, leading to a massive 27% drop in synaptic density, especially in the prefrontal cortex.
So you see, this structural damage, this loss of connections, sets the stage for the chemical imbalances we've been talking about for decades.
The famous dopamine hypothesis, it fits right in. Too much dopamine activity in the striatum helps drive those positive symptoms. And the glutamate hypothesis, it suggests that problems with NMDA receptors in the cortex are a key driver of the negative and cognitive symptoms. It all starts to connect.
Okay, so let's pull the lens back out again. Now that we've seen the molecular chaos, let's see how these tiny events build on each other over time to create the full clinical picture of the illness.
And you know what? The timeline of the illness maps perfectly onto the pathophysiology we just discussed. The prodromal phase, with those subtle changes, is really the slow burn of rising oxidative stress and synapses starting to weaken. Then, bam, the first psychotic episode often hits right during the peak of normal adolescent synaptic pruning. That's not a coincidence. That's when the process accelerates pathologically. And the chronic phase, well, that reflects the long-term damage from all that lost connectivity. So clinically, we organize all of this into those key symptom clusters for diagnosis. You've got your positive symptoms, things that are added, like hallucinations. You've got your negative symptoms, things that are lost, like motivation and social connection. And then you have the core cognitive problems. And just like with our patient, the age of onset shows a clear difference, typically hitting men a bit earlier than women.
Okay, we've talked a lot about what goes wrong. So what can we do about it? Let's connect all this pathophysiology directly to our treatment strategies, both what we have in our toolbox today and what's coming down the pike. For the last 70 years, our pharmacological playbook has been all about dopamine. Our frontline typical and atypical antipsychotics are really good at blocking the D2 receptor, and that's incredibly effective for those positive symptoms. The atypicals add a little something extra, serotonin receptor blockade, which can help a bit with negative symptoms and often comes with a better side effect profile. But here's where it gets really exciting. The future of treatment is about going upstream, targeting the root causes we've been talking about. I mean, just imagine therapies that could dial down that complement cascade to prevent overpruning, or treatments that could calm down those hyperactive microglia. Or what if we could actually enhance mitochondrial function and fix the energy crisis? This is where the research is headed, and it's incredibly promising. And finally, and this is so important, we have to remember that we are not just treating a brain. Schizophrenia's impact is felt throughout the entire body, and it absolutely requires us to treat the whole person. The reality is, patients with schizophrenia have sky-high rates of cardiovascular disease, metabolic syndrome, you name it, and that directly contributes to that shocking 10 to 25-year drop in life expectancy. Beyond the physical toll, the illness can be devastating to a person's social and work life, and it places an unbelievable strain on both patients and their families. And that brings us to our final, forward-looking question. We are on the cusp of moving beyond just managing symptoms. As we get this crystal-clear picture of the molecular cascade, the energy failures, the synaptic pruning, the next great frontier has to be prevention. So the real question is, how can we translate all this knowledge into proactive, truly neuroprotective strategies to help high-risk individuals before psychosis ever has a chance to take hold? Always stay patho-curious. Disclaimer, not intended for medical diagnosis or advice, purely education only.